Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor in the University of Delhi. Today, we are going to discuss about the module Magnetic Force Microscopy, in which we are going to discuss data analysis, and this shall come under the paper of Surface Analytical Techniques, Part 1. When we complete this module, you will be able to understand to a great extent about the introduction, then results and conclusions. Frequency response of cantilever. There are two diagrams given. One is amplitude towards drive frequency. The other is phase versus drive frequency. Change in the magnetic force on the tip produces changes in resonance frequency, amplitude or phase of cantilever oscillations. All measurable properties can be measured possibly here. Typical amplitude variation of 10 to 30 nanometers and frequency shifts of 1 to 100 hertz can be varied. And here in the figure, red lines indicate no magnetic forces are there, and dashed or dotted lines indicate the measurements with magnetic force.
Recent remarkable progress in magnetic resonance imaging (MRI) naturally raises the question about the ultimate possibility for atomic scale MRI resolution single spin detection. However, the MRI techniques are based on the phenomena of electromagnetic induction, which implies the detection of a microscopic number of spin. The minimum number of nuclear spin detected by MRI techniques is about 10 to the power 12, and the minimum number of electron spins detected using electron spin resonance (ESR) techniques is about 10 to the power 7. To resolve the problem of a single spin detection, slides suggested using the force detection techniques like those used in atomic force microscopy (AFM). However, the magnetic force is much smaller than electric force detected in AFM. In order to overcome this difference, slides proposed a combination of magnetic resonance techniques for a single spin with the mechanical resonance of an ultra-sensitive cantilever. According to this idea, a ferromagnetic particle attached to the cantilever tip will experience a magnetic force produced by a single spin. If the frequency of the spin oscillation matches the resonant frequency of the cantilever vibration, the spin force will amplify the cantilever vibration, which can be detected, for example, by optical method. This method of a single spin detection was labeled magnetic resonance force microscopy (MRFM).
When we come to introduction, magnetic force microscopy is a special mode of operation of the atomic force microscope. The technique employs a magnetic probe which is brought close to the sample and interacts with a magnetic stray field near the surface. The strength of the local magnostatic interaction determines the vertical motion of the tip as it scans across the sample. Amplitude detection. Again, a diagram has been given, which is frequency versus amplitude, and it detects the amplitude at different values of frequencies. Again, red line here indicates that there is no magnetic forces applied, and dotted line here indicates the presence of magnetic forces. Slope detection here will mean you drive the cantilever to a fixed frequency, W0, slightly off resonance, such that delta A for a shift in resonant frequency, which will be W0 is equal to W0 minus W dash is maximized. This can be calculated with the help of a mathematical relation which has been given here. The way we have done amplitude detection, here phase detection has been shown. Once again, similar kind of diagram is there, which is the plot of phase versus frequency. And there are two lines, red, no magnetic forces, dotted line with magnetic force, and there are mathematical relations given which will indicate the phase detection. Image contrast. It is attractive interactions. We have negative phase shift, then dark image contrast, and similarly repulsive interactions. Again shown here, positive phase shift and bright image contrast have been shown here. The effect of drive frequency on amplitude response. This has been given here in terms of a diagram. Weak response of a resonant frequency is given in number 2 point compared to a slightly off resonance at 1 or 2. Note the contrast reversal between 1 and 3 which has been shown here in the diagram. Bit transition in hard drive media has been shown here for an image which is 25 into 25 micrometers. Mfm was introduced shortly after the invention of the AFM by Martin and Vikramasinghe in 1987 and became popular as a technique that offers high image resolution without the need for special sample preparation or environmental conditions. Since the early 1990s, it has been widely used in the fundamental research of magnetic material as well as in the development of magnetic recording components. This detects the quantity that is of particular interest for the magnetic recording processes, namely the magnetic stray field produced by a magnetized medium or by a right head. Nowadays, the main developments in FMF are focused on the quantitative analysis of data, improvement of resolution, and the application of external field during measurements. This was done by Schwartz and Weizen-Danger 2008. The interpretation of images acquired by MFM requires knowledge about the specific near-field magnetostatic interactions between probe and the sample. Therefore, this subject will be briefly discussed hereafter. That is, what way the interaction will be monitored and what are the changes. Other topics to be considered are of the properties of suitable probe, the achievable spatial resolution, and the inherent restriction of this particular method. More detailed information can be found in articles by Ruger et al., Orthon et al., or Hartman, etc. Valuable information can also be found in the work of Koch and Hendrich et al. In the present chapter, we will also demonstrate some applications of the technique made by our research group in the study of magnetic vortices formation in a sub-micro-sized structures, as well as further magnetic properties of silicon and germanium-based magnetic semiconductor thin film. More tips on selectable moment and coercivity. High moment and high sensitivity tip. We have coercivity 30 MT, magnetization of 300 Ka/m, tip radius is 50 nanometers, and similarly we have low moment high resolution tips. These are magnetization of 80 Ka/m, tip radius is 15 nanometers, and coercivity 12.5 MT. This has been given in this diagram. If the stray fields from the sample are high or the tip coercivity is small, the sample can re-magnetize the tip, which has been shown here. High tip coercivity prevents surface-induced remagnetization of the tip magnetization. It has been shown by a relation here. If the tip magnetization is high or the sample coercivity is small, the tip can remagnetize the sample. It has been shown here in the diagram. Low moment tip can prevent tip-induced remagnetization of surface magnetization. Tip effects. It has given a diagram where the non-contact mode has been used, and then magnetic lines of forces measured using electron holography for Mfm tip with a tip radius of 30 nanometers has been there, magnetized along with the axis of tip z direction. B tip near the surface, then B tip at the distance of 10 nanometers have been shown. Field of distance is 2 tip radii away from tip is approximately dipolar. So this has been shown here with tip fields effect. The paper which has first used this, that reference has also been shown here for the benefit of the learners. It indicates what way we can plot force calibration plot. At constant point, there is an abrupt change in the slope. At this point, the cantilever has begun to feel the surface forces. In tapping mode, feedback is set to maintain amplitude just below knee of the curve. If in the lift mode, the Z piezo is offset, so cantilever is operating just above the knee. Qualitative interpretation of Mfm images. Here, these images have been given Mfm images of magnetite grain with the direction of the magnetization nearly parallel to the surface of grain, as indicated by smaller contrast between domains. High contrast alternating polarity domains, walls, subdivided walls have been given in these block lines. Magnetization nearly parallel to the surface of grains, as indicated by similar contrast between domains, have also been given. Qualitative interpretation of Mfm images. Two images have been shown here for the benefit of learners. MF images of magnetite grain with directions of magnetization oblique to the surface of grain, as indicated by different contrast between domains. Two photographs have been given, and the reference to has been indicated there. Slide number 17 gives the qualitative interpretation of Mfm images. Exsolved magnetite inclusion in silicates has been taken and shown here. Results. As confirmed by the Raman measurements, as the thermal annealing advances, the SIMN samples show crystallization signals along with the growth of randomly dispersed sub-micrometer structures on the surface of the film. These structures are manganese-containing silicon crystallites surrounded by silicon crystals in all the directions, amorphous silicon and MnSi 1.7 silicide phase. AFM and FM images of the sputter deposited SIM 20% film after thermal annealing at 600 degrees centigrade. The AFM scanning was performed in the tapping mode, whereas MFM in the lift mode by means of a cobalt chromium coated tip magnetized just before scanning. The measurements were carried out under room conditions, that is, temperature and atmosphere shall be obviously fixed, from a 1.7 micrometer thick film deposited on the crystalline silicon. Drawing of the magnetic moment configuration for ferromagnetic tridimensional sub-micrometer structures have been shown here. At these very small dimensions, the magnetization adopts the pattern of a curling spin or magnetization vortex. In this curling arrangement, the spin directions change gradually in place or in plane in order to maintain the exchange energy and to cancel the total dipole energy. This has been shown in this slide very effectively. The obtained magnetic contrast, which occurs because of the changes in the magnetization orientation along the sub-micrometer structures. In other words, the presence of these manganese-based structures, probably magnetic or manganese dimmers, in combination with the manganese-silicon 1.7 phase, can lead to the appearance of magnetic activity. But Nardini et al. In 2004 had done this. Then Afauda et al. In 2006 did the same, whose main characteristics are highly influenced by the size and shape of the structure. It is interesting to observe the quite different topographic, that is AFM profile, and magnetic MFM voltage arrangements achieved from the very same structure exclusively due to the presence of magnetic activity. The effect of manganese on the formation of these magnetic vortices is also remarkable, describing that once the structure is obtained, the Mn distribution, that is manganese distribution, is non-uniform and or highly influenced by the presence of manganese sulfide 1.7 phase around it. MFM signal, as obtained from the voltage differences at the bare substrate film edge region, see sketch, as a function of the magnetization of saturation as obtained from the squid measurements at temperature greater than equivalent to 300 degrees Kelvin. The MFM data correspond to three different MFM tip to sample distances, that is D is equal to 200, then 1000 and 2000 nanometers. The measurements were carried out on the GeMn 3.7% and GeMn, that is germanium manganese 24% films, that is either germanium manganese 3.7% and the other is germanium manganese 24% films deposited on crystalline quartz, both amorphous as deposited, and after crystallization at the temperature indicated in the figure. The lines joining the experimental data points are just guides to the eye, as shown in this figure given below. Here, magnetization of saturation point versus MFM signals in millivolts have been given, and magnetization has been given in the units of EMU per cubic centimeter in terms of volume, if one measures the three dimensions. These diagrams, these plots which are there for D 200 nanometers, then 1000 nanometers, and in terms of triangle, it is 2000 nanometers. So three different plots, 200 nanometers, 1000 nanometers, and 2000 nanometers have been shown here, which indicates the variations. The experimental data indicates that the MFM signal decreases with the distance d, demonstrating the magnetic character behind the interaction between the MFM tip and the sample. except for minor deviations in the magnetic force microscopy. The Mfm signals obtained with the lowest D values, which were clearly affected by the experimental conditions, can be obtained.
Application of magnetic force microscopy studies in bulk polycrystalline iron. Magnetic force microscopy studies on the effect of crystallographic orientation and external magnetic field on magnetic microstructure in a bulk polycrystalline iron specimen. The magnet crystalline anisotropic effect on the domain structure is characterized with the spot of electron backscatter diffraction study. The distinct variations in magnetic domain structure are observed based on the crystallographic orientation of the gain surface normal with respect to the cube axis, the EG axis of magnetization. Further, the local magnetization behavior is studied in situ by Mfm in presence of external magnetic field in the range of -2000 to 2000 OE. Various micro-magnetization phenomena such as reversible and irreversible domain wall movements, expansion and contraction of domains, Bark-Hussein jump point of a pane domain wall and nucleation of a spike domain are visualized. The respective changes in the magnetic microstructure are compared with the bulk magnetization obtained using vibrating sample magnetometer. Bowing of a domain wall pinned at 2 points upon application of magnetic field is used to estimate the domain wall energy density. The Mfm studies in presence of external field applied in two perpendicular directions are used to reveal the influence of the crystalline anisotropy on the local micromagnetization. A new variable external field magnetic force microscope is introduced here. The most outstanding feature of the system is its capability to perform stable images under a variable external magnetic field that can be applied both in plane and out of plane direction. The performance of the microscope are illustrated for four different stable selected samples: highly oriented pyrolytic graphite, longitudinal magnetic storage media, iron platinum thin film with in-plane anisotropy, and nickel nanowire with axial EG axis embedded on the ceramic matrix. The use of this variable field magnetic force microscope as a magnetic writing reading technique. The application of a magnetic field during the Mfm operations modifies the magnetic state of the tip as well as of the sample. In each case, the effect of the field depend on the relationship between the maximum applied magnetic field and their corresponding coercitivities. Basically, in particular, it can be used to reverse the magnetization of both tip and sample. In addition, the evaluation of the Mfm signal versus the externally applied magnetic field can be used to obtain the hysteresis loop of the sample or hysteresis loop of the Mfm probes. The Mfm system presented in this work is particularly useful for such a relevant objective due to its mechanical stability.
So, students, after having studied about magnetic force microscopy and the way images are formed, we have dealt with data analysis in this particular module. And you have seen the importance of this as well as the preparation of surface data, which has been studied with the help of this. Magnetic force microscopy can be very properly summarized when we talk about this module, and I'm sure when you read the summary, you will be able to appreciate this much better. So, therefore, it can be summarized as magnetic force microscopy image of an isolated submicrometer structure present in the SiMn 20% film after thermal annealing at 600 degrees centigrade is checked. Its height profile as obtained by AFM and at 600 degrees centigrade. Its height profile as obtained by AFM and corresponding Mfm voltage along the horizontal, vertical and diagonal dashed lines drawn in A are represented, and in B and C and D also are given respectively. Note that Mfm voltage pattern due to the presence of magnetic vortices in the structure will find it little more difficult to record. It is interesting to observe the quite different topographic, that is AFM profile, and magnetic MFM voltage patterns achieved from the very same structure exclusively due to the presence of magnetic activity. The effect of manganese on the formation of these magnetic vortices is also remarkable, suggesting that once the structure is formed, the Mn distributed is non-uniform and or highly influenced by the presence of MnSi 1.7 around it. The Mn-free GeMn 3.7 and GeMn, that is germanium manganese 24% film deposited under crystalline quartz substrates were also investigated uh, around it. The manganese-free GeMn 3.7 and germanium manganese 24 point film deposited under crystalline quartz substrates were also investigated through similar magnetic force microscopic measurements, which was originally done by Ferry et al. In 2010. Therefore, since the samples showed a flat surface, the magnetic activity of these three films was evaluated by scanning the MFM tips along at 20% or 20 micrometers line across the crystalline quartz substrate, partially covered by the desired germanium film. By adopting this procedure at the bar substrate film edge, the MFM tip will experience a signal difference which is proportional to the magnetic response of the probe region. Now, considering that the crystalline quartz gives no magnetic contrast in the MFM measurements, the observed MFM signals is exclusively due to the germanium manganese film. In fact, and in accordance with the literature, Cho et al. In 2002 and Squid results, no MFM signal has been observed from both the amorphous and the crystalline manganese-free germanium films. Also, in order to confirm that the MFM signal is mainly of magnetic nature, this is what was confirmed by Porthon et al. In 1998. The measurements were carried out at a fixed tip to a sample. This was carried out at a fixed tip to sample, that is substrate plus film, distance d in the 100 to 2500 nanometer range. The main result of these MFM measurements in conjunction with the SQUID data are shown in figure 11. Here it is important to point out that similar results were obtained for the SiMn samples according to this procedure. The MFM measurements for the cobalt-free silicon and germanium films, both amorphous and annealed up to the crystallization temperature, suggests that the absence of magnetic activity is not there. Magnetic activity is absence. It can be judged from this. The experimental result, as expected, since it was also observed in the set of magnetic-free silicon and germanium samples, as I said, was done by Ferry et al. In 2009 and 2010, and is in accordance with the literature, that is Boldock et al. In 2005, Cho et al. In 2002, etc., was done. When annealed at high temperatures, the XRD results indicate the presence of non-magnetic phases in the film containing cobalt. In addition to this, it is known that cobalt is less efficient than manganese, promoting ferromagnetic alignments, and a high magnetic moment for the case of germanium. Conizena et al. In 2006 had done the same thing. Therefore, we expect a similar magnetic behavior from the cobalt for the silicon matrix. I hope this would have made the data analysis part very clear to you. Thank you very much.